Our next speaker is an additional faculty member who has become affiliated with CERIAS just within the last few months. So my great pleasure to introduce Zahra Ghodsi, who is a assistant professor in the electrical and computer engineering department here. Welcome.
Thank you for the introduction. Hello, everyone. I'm very excited to be here. This is my first CERIAS Symposium, and it's wonderful to be part of this very vibrant community. So I'm going to talk to you about collaborative learning, specifically the security issues that exist in enabling such applications, what we've learned based on our work so far on these systems, and what I think the vision for the future would be. So I don't need to talk about the importance of machine learning to this audience. You're all familiar with the great advancements in this area, the impressive results that they got in what now is traditional image recognition, but also more interesting new applications in enabling language models, or for example, designing chips and everything else. The issue here is that if we look at the pipeline of this systems, we have multiple steps, right? So at a high level, we have to acquire usually a large amount of data. We have to have this training algorithms and then eventually deploy them in practice. So each of these steps have its own characteristics. So usually the amount of data that we require for training is distributed among a large number of users. The amount of computation resources required for training these models is massive. So for the not even the largest language models, we would require months of computing on a GPU servers, essentially. And finally, we once for a large class of applications, we would have to enable real-time inference, which could be difficult due to the scale of these models. So this creates a very complex ecosystem of different parties that hold the data, that hold computing power, or hold the trained models. And these different parties would then be required to collaborate with each other to perform a learning task, right? Obviously, this creates a lot of security issues. The security issues could be related to the privacy of the data of different clients and users, the intellectual property IP rights of these models that are very difficult to train, the safety or integrity of these computations, specifically if you're dealing with safety critical applications, autonomous vehicles, and things like that. So we have to ensure that these frameworks are robust against either intentional or accidental errors. So our research is on providing rigorous guarantees on all of these desired properties that we want within these learning frameworks, while at the same time ensuring that we have high accuracy and low overhead for practicality. So as part of this talk, my goal is to convince you that the way to approach this problem is to co-design and optimize all of these systems at various levels, be it the cryptographic protocols that give us the assurances, the machine learning models, as well as the underlying hardware infrastructure that these things run on. So we started by looking at the outsourced inference problem. And the privacy issues that are involved in that. So in this setting, we have a server with a trained model. We have a client with an input. The client wishes to perform an inference computation on the server's model. The assumption is that the client's input can be sensitive. On the other hand, the server's model is also proprietary, so the server may not wish to release their model publicly. So we want to enable this computation without the server learning anything about the client's input and without the client learning anything about the server's model. Now we have protocols in cryptography that allow us to do this collaborative computation between the client and the server for this inference specific task. Unfortunately, the costs here are very large. So one of the recent frameworks that came out for a single inference computation of, let's say, classifying an image, it takes 40 seconds of online runtime, and it requires around 40 gigabytes of both communication and storage. So obviously, this is not achievable for a bunch of different applications to be implemented. Now, if you look at the computations that exist as this private inference, we have various layers in our neural networks, for example, right? So we have linear layers, nonlinear layers. And it turns out that the bottleneck for doing this private inference computation in the private domain is dominated by evaluating the ReLU layers privately. So in part of our work, CryptoNAS and DeepReduce, we looked at reducing the number of ReLUs. And in the follow-up work, we reduced the cost per ReLU evaluation in these models. So collectively, we were able to reduce this the runtime and communication and storage requirements by an order of magnitude. So at a high level, the best solutions that exist for doing this private computation use different primitives for different layers. So we have different cryptographic primitives for securely evaluating the linear layers, and other primitives for nonlinear layers. So in this case, as an example, you can use secretary and homomorphic encryption for the linear layers. And as it turns out, a bulk of the computation can be moved to an offline pre-processing phase. So the computation that is performed when the input is available is actually very efficient. Unfortunately, this is not the case for nonlinear layers. So the protocols that can compute these nonlinear evaluations, such as garbled secrets or oblivious transfer, they tend to be expensive both in online and offline stage. So we benchmark the runtime, the online runtime of this protocol that I just discussed. And as you can see, more than 98% of the computation is dominated by just evaluating the ReLU layers. And this is in stark contrast to the profile of runtime for these models in the non-private world, right? So when we try to design models, what we do is we want to find the most accurate model for a number of flops or floating point operations, because in the regular world, if we don't care about privacy, the heavy competition is on the linear layers. Comparisons doing ReLU computations is effectively free. So because this characteristic is so different, our suggestion was that we need to now design models that would be the most accurate for what we call a ReLU budget. And this is what we did in our work. We looked at the existing models. If you grab off-the-shelf models, they use ReLUs indiscriminately because they're effectively negligible. So what we did is we introduced optimizations to reduce this redundancy and bring down this cost, what we call ReLU shuffling, pruning, and balancing. And we combine this with a neural architecture search method to find the best models. We call this framework CryptoNAS. Where I'm not going to go through the details of this framework, but I'll just show you a snapshot of the results that we were able to get. So as you can see, the models that our CryptoNAS framework is able to find lie at the parallel frontier of the accuracy and runtime. So more interestingly, even compared to models that are designed for embedded devices or constrained devices such as mobile nets, we're able to find models that would work better in the private domain. So CryptoNAS started a line of work on designing models that are ReLU efficient, specifically for the private inference task. Other people have worked on it. We've also did follow-up works. This appeared at ICML. And we were able to reduce this 44-second runtime down to 5.4. In the next follow-up work, we then looked at the specific computation that is required for evaluating each ReLU and further reduced that. Now, this optimization is possible, but because we acknowledge that neural networks inherently are robust to certain types of faults. So let's look at how we can actually leverage this understanding in reducing this cost. The protocol that is required for evaluating the ReLUs, for example, in this case, what is known as the garbled circuits in cryptography, requires your representing the computation as a Boolean circuit. The details here are not important, but what I want to convey is that evaluating this circuit by itself, it can be very expensive. So you would require 12 kilobytes of both storage and communication for a single ReLU. So you have millions, hundreds of millions of ReLU per model. So you can see how this cost can quickly add up. Our first optimization here was that we recognized that we can effectively drop some of the components here. So for those who are interested, these computations are performed in a finite field usually. So you have to do a bunch of modular operations. What we did effectively is to kind of drop this expensive computations here. Now, this new circuit is not exact, right? So in fact, we characterize the fault rate of this new implementation. And we show that this is a probabilistic fault rate with a probability that is proportional to the magnitude of values over the size of this field, which is represented by a graph. So the point here is that now we are able to reduce the size of this circuit from 12K to 9K, and we're incurring some error, but I'll later show you that this error doesn't actually translate into effects in accuracy. Similarly, we truncated. You can truncate the inputs to this circuit. Again, this optimization would incur faults that are proportional probabilistically to this value, but enables us to reduce the size of the circuit further. Now, to understand the effect of these faults, we can take a look at the ranges of values that you see within the layers. So here I'm showing you a distribution of the inputs to a ReLU layer. And what I want to say is that if we look at these faults that appear for these types of optimizations that we had, we either have faults with high probability over small values, or we have low fault rates for the rest of the values that we have. So collectively, the effect of these optimizations that we further reduce the cost with less than 1% accuracy drop in the networks that we train on. So I've talked about inference computation. I'll quickly talk about the challenges that exist in collaborative learning. In this setting, we want to have multiple users with their data train a global model between each other. And usually this setting is referred to as a federated learning. And in this case, we want to ensure that the privacy of the data holders is preserved. But also, we want to guarantee that not a malicious user is not able to derail the training. So in this setting, the clients are submitting their updates only, but it turns out that the update values themselves could reveal information about the private data sets. So in order to perform this, we'll have to do a private aggregation, essentially. I'll skip the details of this. The main idea is that the clients are going to send a masked version of their updates to the server for aggregation, which in this case, the server would not learn anything about the individual update values, but would be able to obtain the final aggregate results to update the model. The problem in this case is that now the malicious clients can potentially insert targeted attacks or just out of bound updates to derail this training process. So how do we enable the server to perform checks on the updates without revealing the values or leaking anything about the updates themselves, because they contain information about the private data? Our solution here is to use zero knowledge proofs. So in addition to sending the mass updates client, we'll also send a proof of the well-formedness of their update, as well as the correctness of the computations that they've done. So we show that actually with our setting, we are able to protect against a wide range of attacks, poisoning attacks, while at the same time the overheads are low with a bunch of different optimizations that we implemented without that I won't go over the details here. So just to wrap up, what I want to say is emphasize the age-old lesson that security cannot be an afterthought, right? So if we want for this, especially for these systems that have such a massive scale, if we want to be able to provide all of these guarantees on privacy, security, robustness, etc., for the leaps of gains, improvements that are required for practical systems, we'll have to work at the intersection of these different levels of the stack in order to get closer to something that we can call a practical system. So as I mentioned, with co-designing machine learning and cryptography, we're able to reduce orders of magnitude. We'll probably need a couple of more orders of magnitude to actually start seeing these systems practically. Similarly, we can have hardware help crypto and other way around. So we have worked on projects that allow in a setting where you have like an accelerator that is manufactured by a fab that is not trusted, you can use these cryptographic protocols to ensure the correctness of the computation with the possible existence of a hardware Trojan, for example. Similarly, we have projects on helping on hardware helping cryptography, so accelerating these cryptographic protocols on FPGAs, and more interestingly on GPUs that are widely accessible. And finally, going beyond these more traditional learning frameworks, looking at emerging paradigms. For example, graph neural networks that have worked really well in applications such as drug discovery and so on. The challenges can scale because you have like millions of nodes, in this case, billions of nodes. You'll have to find a way to efficiently map these to the hardware infrastructure that you have. And also now you have multiple clients involved, multiple users, and every computation would involve a large number of users. So efficiency problems and security issues manifold here extensively as well. I'll leave you with this. I think that for guaranteeing all of these requirements for these learning frameworks that we have no way other than looking at all of the stacks layers at the same time and bringing people from these different communities together. Thank you.
Thank you, Zahra.